How big can a mind be? Not in the poetic sense, not open-minded or narrow-minded, but in the literal, physical sense. If your thoughts, your memories, your entire sense of self are what a brain does with a trickle of energy, how far could that be pushed? Your life is powered by about 20 watts. That's the power of a dim household light bulb, humming quietly in the corner of a room. And yet, from that tiny flow of energy, your brain somehow maintains a living, ongoing simulation of reality. It remembers your childhood, it predicts your future, it worries, it hopes, it dreams. 20 watts. That's the budget for everything you have ever loved or feared or understood. So here's the question we're going to walk into together today. If a mind is just what happens when matter and energy are organized in a certain way, how big could a mind become if you gave it not 20 watts, but the full power of a star? Or a whole solar system? Could you build a planet-sized computer? A Dyson brain, wrapped around the sun, thinking with every photon? And if you did, what would that even mean? Would that mind be unimaginably wise? Would it experience time differently? Would it care about us at all? I'm Rowan K, Mercer, and this is the Science Audit. In this episode, we're going to stress test some of science fiction's grandest ideas, Dyson spheres, Matrioshka brains, galaxy-scale computers, against the hard edges of real physics, thermodynamics, information theory, and gravity. Along the way, we'll keep circling back to something very small and very personal. What all of this says about your mind, my mind, and the fragile islands of thought we carry around inside our skulls. To start, we need to say something that sounds obvious, but is easy to forget. Computation is a physical process. We're used to thinking of information as this ghostly, weightless thing. You store photos in the cloud, you stream videos from the internet. Your memories feel like they float in your head as stories, not as molecules. But underneath the metaphors, every bit of information is a physical pattern. A bit, the basic unit of digital information, is just a system that can be in one of two distinguishable states, like a coin that's either heads or tails, a light that's on or off, an electron that's here or there. When you flip a bit, you change something in the physical world. Your brain is doing this all the time. Every thought you have corresponds to a specific pattern of neurons, brain cells, becoming electrically active or quiet. A neuron is like a tiny, biological transistor, integrating inputs from thousands of other cells and then, if it crosses a threshold, firing an electrical pulse. You have about 86 billion of these neurons, each with up to thousands of connections. When scientists try to estimate how much computation your brain does, they often look at how many of those neural signals fire per second. The rough estimates vary, but one common ballpark is around 10 to the power of 14 to 10 to the power of 15 operations per second. That's 100 trillion to a quadrillion elementary updates happening in your head every second, running on the power of that single dim light bulb. Operations per second isn't consciousness, but it gives us a way to compare very different systems using the same yardstick. Think of it like this: your inner universe, your model of reality, your ability to learn a language, to fall in love, to imagine a future, is built out of a staggeringly dense storm of tiny physical events, tens of trillions of them each second, all orchestrated by chemistry and electricity, all paid for in energy. And here's the key: every one of those tiny events has a cost. Not a moral cost, a thermodynamic one. There's a principle in physics called Landauer's principle. It says, roughly, that whenever you erase one bit of information, whenever you take a system that could have been in multiple possible states and force it into one definite state, you must generate at least a tiny amount of heat. That's the thermodynamic price tag for forgetting. We can think of it like this: imagine your computer is a very tiny librarian. Every time it wants to reuse a page in its notebook, it has to erase what's there. Erasing isn't just nothing happens, it's an active process. You take a system that had many possible configurations and compress it down into a smaller set of possibilities. That squeezing of possibilities is, at the microscopic level, a kind of shredding of order, and it shows up as heat dumped into the environment. Landauer's principle puts a lower bound on the energy cost of one bit of erasure, about KTLN2, where K is Boltzmann's constant, a tiny conversion factor that links temperature to energy, and T is the temperature in Kelvin. At room temperature, that minimum cost is on the order of 3 times 10 to the power of negative 21 joules per bit erasure. That is unimaginably small. But when you're dealing with billions and trillions and quadrillions of bits, that tiny cost adds up. Now, our real computers and our brains are incredibly wasteful compared to this absolute theoretical minimum. We're nowhere near Landauer's limit in practice. But the existence of that limit tells us something deep. Information is not free. Thinking is not free. In this universe, if you want to perform logical operations, if you want to erase old states and write new ones, you must exchange energy and generate heat. And information doesn't just cost energy. It takes up space. Every bit of information has to be encoded in some physical system, in the position of atoms on a hard drive, in the orientation of magnetic domains on a tape, in the structure of molecules in DNA, in the pattern of synapses in your brain. There is no such thing as abstract, disembodied data. If it exists, it is literally written into the world. You can increase how tightly you pack that information. We've gone from punch cards to magnetic drives to flash memory, and experimental systems go even further, using single molecules or quantum states. But there are hard limits. Pack too much energy or matter into too small a space, and gravity starts to care. Pack even more, and you risk making a black hole. So already, just with this basic picture, we can begin our audit. If a mind is a physical process that manipulates information, and if information has a minimum energy cost to erase and a maximum density before gravity collapses it, then physics is quietly whispering, there is a maximum size, or at least a maximum capacity, for any mind that can exist in our universe. Before we jump to stars and galaxies, let's zoom out just one level, from your brain to our machines. Modern data centers, the physical backbone of the cloud, draw megawatts of power. A single large facility can use as much electricity as a small town. Inside, rows upon rows of servers are flipping bits at astonishing rates, doing everything from streaming video to training massive AI models. If you've ever felt a laptop get uncomfortably hot on your legs, you've experienced the central engineering problem of computation: waste heat. Almost all of the electrical energy going into a processor ends up as heat that has to be removed. If you can't get that heat out quickly enough, the temperature rises, the materials degrade, and the chip fails. This is why the limiting factor for how fast we can run current computers isn't just the number of transistors, it's cooling. A high-end gaming GPU, pushed to its limits, can glow like a small space heater. We have to strap on fans, radiators, sometimes even liquid cooling systems just to keep them from cooking themselves. And this brings us to a crucial insight. What stops your laptop from becoming starbright is not a lack of imagination. It's thermodynamics. If you pump too much power into too small a volume, you're building a tiny sun that melts itself. So if we want to ask, how big can a mind be? We have to invert the problem. Instead of cramming more power into the same space, what happens if we expand the computing substrate to truly astronomical scales? What if we build a computer as big as a planet? As big as a solar system? This is where the idea of a Dyson sphere enters. In science fiction, a Dyson sphere is often depicted as a solid shell around a star, like a giant ball with the star in the middle. In reality, such a rigid shell would be structurally absurd. It would collapse under its own gravity or drift into the star. The more realistic version, originally contemplated by physicist Freeman Dyson, is a swarm, countless satellites or habitats in orbit, collectively capturing a significant fraction of the star's energy. So think of a Dyson swarm as a vast, three-dimensional cloud of machines encircling a star, each one sipping sunlight, turning it into useful work, and radiating away waste heat. It's less a sphere, and more a fog of civilization. How much power are we talking about? Our sun outputs about 3.8 times 10 to the power of 26 watts. That's 380 septillion joules of energy every second. Right now, human civilization uses on the order of 10 to the power of 13 watts, tens of trillions of watts. So a complete Dyson swarm around the Sun could, in principle, give you about 10 trillion times our current global power use. Remember your 20-watt brain. If you could allocate the Sun's entire output to running brains with similar power budgets, you could support roughly 10 to the power of 25 human-equivalent brains. That's more minds than there are stars in the observable universe. Of course, those would be human-style biological brains, with all our inefficiencies and quirks. A technological civilization might design much more efficient computing substrates, denser memories, faster logic gates, lower energy per operation. So instead of, how many human brains? Let's translate that solar output into a more neutral currency, operations per second. If you could somehow operate right at the Landauer limit at room temperature, which we absolutely cannot today, but this gives an upper bound, then each joule of energy could, in theory, erase on the order of 10 to the power of 20 bits. Multiply that by the Sun's power, and you get something like 10 to the power of 46-bit erasures per second. That's a 1 with 46 zeros. That's the ceiling for how much logical work you can squeeze out of a single star, if you are unimaginably good at engineering and operate near fundamental thermodynamic limits. In practice, you'd do much worse, but the point of this audit is to understand what's theoretically possible, not just what's practical for us in the 21st century. Now, a Dyson swarm that simply collects the star's energy and uses it once already gives you a stupendous computing budget. But futurists and theorists have pushed the idea further, to something called a Matrioshka brain. The name comes from Matrioshka dolls, those nested Russian dolls where each one fits inside a larger one. A Matrioshka brain is a series of concentric Dyson shells or swarms around a star, each layer capturing the waste heat of the one inside it. Here's the logic. When you run a computer, you take in low-entropy energy, a kind of ordered, useful energy, and you spit out high-entropy waste heat. The inner layer of your Dyson swarm might operate at, say, hundreds of kelvins. It takes in sunlight at about 5,800 kelvins from the star, does computations, and radiates away its waste heat in the infrared at a lower temperature. But that waste heat is still energy. So you could build a second shell further out, tuned to a lower operating temperature, that absorbs the infrared radiation from the inner layer, does more computation, and radiates away even cooler waste heat. Then you add a third layer around that, and so on. Each successive shell uses the degraded energy from the layer below it, squeezing more computation out of the same initial flow of starlight. In the idealized limit, this stack of shells approaches the thermodynamic efficiency of a perfectly staged heat engine. So a Matrioshka brain is not just a star-powered computer, it's an attempt to get as close as possible to the maximum computational output that a star's energy can support. It is the concept of, how big can a mind be? Taken almost to the physical extreme of a single star system. At this point, it's tempting to drift into pure fantasy. Picture this, a shell of machines the size of Earth's orbit, humming with thought. Inside, a star blazing at hundreds of thousands of times the intensity of a noonday sun on every square meter of collector. Further out, colder shells, layers upon layers, all participating in one vast, integrated computational structure, a star-sized mind. What would such a mind think about? Would entire civilizations live as simulations inside it, never knowing that their universe is just a tiny subroutine in a computation bigger than worlds? Would it spend 1,000,000 years contemplating prime numbers? Would it reach for new physics, trying to hack the rules that bind it? That's the story. Now let's audit it. We've already seen that computation costs energy and produces heat. There's another layer, temperature and speed. To operate closer to the Landauer limit, you generally need lower temperatures. Remember that KT term, the energy per bit erasure scales with temperature. So the colder your computer, the less energy it must dissipate for each bit of information it irreversibly throws away. But colder systems are harder to maintain. Cooling itself costs infrastructure. And there are trade-offs with speed. If your signals propagate at finite velocities, which they do, limited by the speed of light and the material properties, then as you make your computer physically larger, it naturally becomes slower in terms of how quickly distant parts can coordinate. Imagine trying to run a single, synchronized clock across an entire solar system. Light takes about 8 minutes just to travel from the Sun to Earth. A signal sent from the innermost part of your Matrioshka brain to its outermost shell might arrive tens of minutes or hours later. That means no single thought could involve tightly coupled computations across the whole structure at once. You'd have to organize it into quasi-independent regions, communicating more slowly with each other. So immediately, we run into a reality check. You cannot have infinitely fast, perfectly efficient computation from a finite star. If you want higher efficiency, you cool down and spread out, and your computational reflexes slow. If you want faster coordination across large distances, you're bound by the finite speed of light. Physics is not impressed by our dreams of instant, frictionless thought. Next, consider waste heat again, but on planetary and stellar scales. Every operation you perform, every bit you flip, ends up as heat that must go somewhere. For a laptop, that heat goes into the air in your room. For a planet-sized computer, that heat has to be radiated away into space. The power you can radiate away from a surface at temperature T is roughly given by the Stefan-Boltzmann law. Power is proportional to the area times T to the power of 4. That T to the power of 4 means that, to dump a given amount of heat, you can either have a small area that runs hot, or a larger area that runs cooler. But you can't skip radiating the heat. It has to go out as light, eventually. A Dyson swarm that captures a star's output and uses it for computation must re-radiate essentially all of that energy back into space as low-temperature light. If it didn't, its temperature would just keep rising until things melted, boiled, or evaporated. So the outermost layer of your Matrioshka brain would glow in the infrared, a cold, dim shell shining with the full power of a star. And here's something to notice. That means a true Dyson-scale computer cannot be stealthy. From afar, it would look like a star whose visible light has been significantly dimmed or blocked, but which glows unusually bright in the infrared. In the search for extraterrestrial intelligence, people have actually proposed looking for such waste heat signatures as a way to find advanced civilizations. Now let's push the density. Suppose you don't just want lots of power, you want as much memory and processing crammed into a given region of space as possible. Maybe you want a brain the size of a planet, not a whole solar system. Here, gravity steps in as a stern accountant. There are results from black hole thermodynamics, the physics of horizons and entropy, that place upper limits on how much information can be stored in a given region of space. One important idea is the Bekenstein bound. In intuitive terms, the Bekenstein bound says there is a maximum amount of information, or entropy, which in this context you can loosely think of as the number of distinct internal configurations that can fit inside a sphere of a given radius and total energy before gravity forces that system to collapse into a black hole. A black hole, strangely, is the most efficient information storage device we know of, at least in terms of bits per area. Its entropy scales with the area of its event horizon, not its volume. So if you try to cram more and more matter and energy, more and more potential information, into a region, you eventually hit a limit beyond which the only consistent configuration is a black hole. That tells us something sobering about planet-sized computers. You can certainly make computers as big as planets in terms of diameter. But you can't arbitrarily crank up their density and memory capacity without limit. If you try to store information beyond a certain density, you stop having a computer and start having a tiny region of spacetime cut off by an event horizon. And you may not like what that does to your ability to do useful computation. A black hole might hold a colossal amount of information, but actually using it as a computer, in the usual sense, is at best extremely speculative. We know that black holes radiate slowly, via Hawking radiation. We have strong hints from theoretical physics that information isn't destroyed when things fall in. But whether you can program a black hole the way you program a laptop, that's deep into the fog of quantum gravity. So for our audit, we'll say this: there is a maximum useful information density for conventional matter before gravitational collapse becomes a problem. That means that if you want more storage and more processing, you can't just pack it tighter. Eventually, you must build bigger structures. Extrapolate this to galactic scales. Suppose a civilization manages not just a single Dyson swarm, but many. Maybe they harness a large fraction of the stars in their galaxy, building a network of star-scale minds. Even then, they are bounded. The total energy output of the galaxy's stars is finite. The total amount of matter they can use as computing substrate is finite. Light speed still limits communication between distant nodes. This leads to a haunting question: is there a maximum thinkability to the observable universe? A finite upper bound on the total number of distinct thoughts, or, more precisely, distinct computational steps, that can ever be carried out by any arrangement of matter and energy within the part of the cosmos we can, in principle, affect. Some physicists and information theorists have played with this idea. They use the total mass energy of the observable universe, the Bekenstein bound, and the finite age of the cosmos to estimate an upper limit on how many operations could be performed. The numbers are mind-blowing, figures like 10 to the power of 120 operations over the entire lifetime of the universe. But they are not infinite. Even reality, at its largest scale, comes with a computational budget. Now let's return to our ultimate mind, a computer pushed as close as possible to these physical limits. What would it look like? And more strangely, would it be usable as a mind, in any sense we recognize? Imagine a computing system so dense with energy and information that it sits just at the edge of becoming a black hole. It's blazing hot, radiating stupendous amounts of power just to stay in equilibrium. Or, in another extreme, imagine a sprawling, ultra-cold computational lattice spread across a solar system, operating close to thermodynamic reversibility, using energy almost as gently as physics allows, but taking millennia for signals to propagate from one side to the other. In both cases, you're right up against the constraints of space-time and thermodynamics. In one, your brain risks vanishing behind an event horizon. In the other, your thoughts might take centuries to complete. Here's the paradox: a computer operating right at the physical limits, maximum density, maximum energy use, or minimum temperature, may not be a practical mind at all. You might not be able to get information in or out efficiently. You might not be able to reconfigure it without pushing it over the edge into collapse. You might create something more like a locked box of potential thought than a thinking being. So when we ask, how big can a mind be? We have to distinguish between theoretical capacity and functional, usable intelligence. The ultimate computer, in the abstract, might be a black hole saturated with entropy. But an actual mind, something that processes information, updates its models, learns, plans, experiences, needs room to breathe within those limits. Now step back. We've talked about Landauer's principle and waste heat. We've talked about Bekenstein bounds and black holes. We've scaled from your 20-watt brain to star-spanning Dyson swarms and galaxy-harnessing civilizations. What does this all say about us? First, it tells us something quietly beautiful. Your brain and a hypothetical Matrioshka brain are playing the same game. They use different rules of engineering, different materials, different scales of energy, but the underlying physics is continuous. The same thermodynamic principles that limit a star-sized computer also limit you, sitting here, listening to this, with your dim light bulb of a brain. There is no special exemption for us. We are small minds carved out within the same cosmic constraints that would shape any planet-sized or galaxy-sized mind. Intelligence is not something that floats above physics, it is a pattern etched into the flow of energy and the arrangement of matter. Your thoughts are as physical as starlight, as oceans, as mountains, just vastly more delicate. Second, there is a kind of humility in these limits. It's easy to imagine that a sufficiently advanced artificial intelligence, given enough time, will become effectively omniscient and omnipotent. But omniscience is not on the menu in a finite energy universe with finite information capacity. Even a civilization that turns its entire solar system into a computer will hit thermodynamic and gravitational walls. This doesn't mean such a civilization wouldn't be terrifyingly capable compared to us. But it would still be bounded. There would still be questions it could never fully answer, computations it could never finish, trade-offs between speed and efficiency it could never escape. In a sense, even the greatest conceivable mind is provincial, confined to its light cone, constrained by its energy budget, limited by the geometry of its universe. Third, these constraints invite us to rethink what progress means. If more computation always costs more energy, and if there are strict upper bounds to both, then the story of the future cannot just be an endless upward line of more processing power. Instead, real advancement might look like using finite computation more wisely. Sharper algorithms rather than brute force. Better questions rather than more data. Structures of society and technology that do more with less, that treat energy and information as precious resources to be spent carefully, not just maximized blindly. At the personal level, you already live under a microcosm of these constraints. You can't think about everything. Your attention is finite. Your memory is not a perfect archive. You triage what to care about, what to remember, what to spend your limited cognitive energy on. Civilizations face similar decisions. What do we build data centers for? What do we spend billions of watts of electricity computing? Advertising optimization? Climate models? Art? The physics doesn't tell us what we should value, but it tells us that we are always spending something finite when we compute. Now let's bring in consciousness. Everything so far has been about information processing capacity, operations per second, bits stored, energy budgets. But does a larger, more powerful computer necessarily mean more consciousness? Does a planet-sized brain feel more than a human one? We don't know. We don't even have a settled scientific theory of why a human brain, organized in the way it is, gives rise to subjective experience at all. We can correlate conscious states with neural activity. We can disrupt consciousness with anesthetics, injury, or electrical interference. But the leap from physical process to felt experience remains mysterious. So when we imagine a Matrioshka brain, we have at least two layers of uncertainty. First, how would such a system actually be architected, given the speed of light delays and thermodynamic constraints we've discussed? Second, even if we understood its architecture, what kind of consciousness, if any, would emerge from it? It might be that consciousness, as we experience it, is tied not just to raw capacity but to certain patterns, to specific dynamics of feedback, integration, and information flow. If that's true, a star-sized computer could, in principle, host many smaller, human-like minds, or minds that are very different but still finite in their subjective richness. More capacity might give you more minds, or more detailed worlds, without necessarily increasing the intensity of any one experience. On the other hand, perhaps there are forms of awareness that scale with the size and coherence of the underlying computation. Maybe there is something it is like to be a solar system spanning mind, something utterly beyond our ability to imagine from within our 20-watt windows. If that's the case, then the universe may already be capable, at least in principle, of hosting experiences as far beyond ours as ours are beyond a single neurons. Physics can bracket the possibilities. It says, you may have this much energy, this much matter, this much time. Within those bounds you can shuffle bits in these ways. But the jump from shuffling bits to being someone remains, for now, an open frontier. And then there are the ethics. If a civilization could actually build a Matrioshka brain, turning an entire solar system into a layered computer, should it? On one hand, such a structure could, in principle, support vast populations of conscious beings living in virtual worlds, backup copies, expansions of culture, entire branches of possibility explored in silico. It could be the ultimate archive of a species' history, knowledge, and art, preserved against cosmic decay. On the other hand, concentrating so much of a system's mass and energy into optimized computation might extinguish other forms of life. If you turn your home solar system into a computer, there may be no room left for organic ecosystems as we know them. Oceans, forests, and biospheres might give way to solar collectors and heat radiators. Is that a tragedy or a transcendence? Is a billion virtual civilizations more valuable than one small, fragile, biological world rich with unengineered life? Does the universe care which ways its atoms are arranged? Physics is silent on that. It just enforces the bookkeeping. Then there's risk. A system that dense and that powerful would be enormously fragile in some dimensions, resilient in others. A single catastrophic error in the design of its control systems could mean the difference between a flourishing star mind and a dead shell radiating useless heat. When you gather that much capacity in one structure, you also gather that much vulnerability. So here we are. We started with your 20-watt brain, this little island of thought powered by the energy of a snack. We scaled up to laptops and data centers, to megawatts of computation limited by cooling. We leapt to Dyson swarms and Matrioshka brains, imagining star-powered minds squeezed as close as possible to the limits imposed by thermodynamics and gravity. We acknowledge that even galaxy-scale computers are still finite, still confined within a universe that sets hard caps on thinkability. So, how big can a mind be? The universe allows minds that are astonishingly bigger than ours in terms of raw capacity. A star system converted into an optimized computational structure could, in principle, perform more operations in a second than all the neurons in all human brains that have ever lived, firing for their entire lifetimes. On that scale, our individual minds are like brief sparks. But these minds, too, would be finite. They would obey the same physics that shapes us. They would need to pay energy for every erased bit, to cool their operations by radiating waste heat into the dark, to respect the speed of light when coordinating across distances, to worry about gravitational collapse if they tried to hoard too much information in too small a volume. Intelligence, then, is not an infinite, free-floating essence. It is a pattern carved into matter and energy, always within strict cosmic constraints. Our job, as one small intelligent species in one small corner of one galaxy, is not just to grow the size of our computational footprint, but to understand the boundaries of our reality, and to find meaning within them. So here is the synthesis of our journey. Computation is physical. Every thought has a cost in energy, and leaves a trace in entropy. There are hard limits, set by thermodynamics and gravity, on how much information can be processed and stored in any region of space, from your skull to a solar system to the observable universe. Within those limits, the universe is generous. It permits minds far more powerful than ours. But it does not permit infinite minds. Now, a contemplative takeaway for you to carry. Tonight, when you lie down to sleep, consider your brain as a tiny Dyson sphere. A soft, warm shell of tissue capturing a trickle of chemical energy and turning it into dreams. You have maybe 100 billion neurons, each flickering on and off, each with a thermodynamic cost. You will never read every book, never solve every equation, never live every possible life. Your computational budget is heartbreakingly finite. So the question becomes, what do you choose to think with the energy you have? Which questions do you spend your limited operations on? What do you attend to, remember, imagine? In a universe where even galaxy brains are bounded, the alignment between your values and your finite attention is not a small, personal matter. It is your way of navigating the deepest structure of reality. And finally, the next great question, the door this journey opens onto. We've asked how big a mind can be, and we've seen that size in time and space is always constrained. But minds are also bound to time in another way, through memory, through the stories we tell about our past and our future. So if time itself is, at some deep level, an emergent construct or even an illusion, as some interpretations of modern physics suggest, what does that say about the memories we hold most dear, and the futures we strive toward? If the flow of time is not what it seems, what is a lifetime of thought? That is where we'll go next on the Science Audit.